Hello and welcome to the Common Rounds again. Thank you for clicking on this video. Now, this video is a follow-up from the episode that I did quite a while ago now. In the making of this video, I had to think to myself about what makes a very good ECG video, having seen a few of them myself, and I set up thinking that maybe I could try and make that one video which I could title the one ECG video that you'd ever need. Just isn't very possible. What I will try to achieve in this video is to sort of pick up on some of the very common patterns that you may come across when you look at an ECG. So essentially, all I want to do with this episode today is talk about some patterns and how to read an ECG, how to sort of get the ball rolling. And I may have mentioned this in my last episode, but the value of the ECG comes in pattern recognition. As such, there's so much variation. Normal people, the so-called normal ECG can vary remarkably because there's just so many different variations, and the heart by itself is such a complicated organ, and when you go down to molecular detail and talk about electrophysiology of the heart, it becomes even more intricate. Just before I start, I'll quickly just mention that an ECG only records electrical activity, does not record the actual mechanical action of the heart. Here's a ECG that I've pulled out from lifeinthefastlane.com. It's an excellent website, and all of my diagrams are from their website, and I'd highly encourage you to have a look at this site. Very broad, and it's just a fantastic site for not just ECGs but everything else. In the last episode I talked about these 12 leads and the patterns that they produce. So we have leads 1, 2, and 3, and then we have the chest leads V1, 2, 3, 4, 5, and 6. V1 to V4 is the anterior heart. V5 and 6 starts to get very lateral to the chest, to the left chest wall. And AVR, once again, points from the right arm. AVL is from the left arm. And AVF is towards the foot. And then if you look down over here, lead number 2 is repeated again. Its space being divided by another lead. The reason for that is this is a rhythm strip, and it gives you a rough idea. It helps you determine whether the patient or whoever's having the ECG, it's easier to extract any changes or differences in rhythm, which may become very important in interpretation of the electrocardiogram. When we talk about the ECG, we normally start off by talking about the rate, how many times a heart beats in a minute. As you can see over here, this one ECG waveform represents one heartbeat. So essentially, in this strip, you have 13 different waveforms, and that means in the time that we started over here, all the way to end, we've had 13 beats. To determine I usually use a rhythm strip for this because it gives you a bigger average over a longer period of time. And the other good thing about the rhythm strip is it represents 10 seconds. So essentially, to get the rate, you just multiply what you've counted by 6. And that way, I can tell that this heart is beating at 78 times per minute. And that's how I calculate rate. And the reason I use this is because it has an average of the entire strip rather than relying on how long it takes per beat, which is quite variable. So if you want to count by beat, remember that each of these tiny squares is 0.04 seconds. 5 of these large boxes over here, say starting from here, 2, 3, 4, 5, that's 1 second. So each of these is 0.2 seconds, each of the smaller boxes, and then the tiny boxes 0.4 seconds. You can count it that way. So essentially, you say the time it takes for a beat is 4 plus 4. It's roughly 3 large boxes, that's 0.6, and then 3 tiny minus 1 of these small ones, that's 0.2. So that's 3 big squares, each of the big square is 0.2, so that's 0.6 seconds, and the tiny square, which is 0.04, we have 2 of them, so that's 0.04, 0.068, so it takes 0.68 seconds per beat, and you divide 60 seconds by 0.68. This is very time consuming. It's more reliable in case this rhythm strip isn't equal to 10 seconds. Another way is to sort of look at the patterns and see how many big squares the boxes correspond to. If it covers the area of 5 squares, that's 60 beats per minute. If it covers 4, that is 75 beats. So this would be 60, pardon my handwriting. This is 75. And if it's here in 3 boxes, that's 100. And this is where it becomes that arbitrary divide between normal rate and tachycardia. And then 2 boxes, that's 150. 1 box, which is 300. Aha, now you laugh at me and say, a rate of 300, that's impossible. But we might actually look at that once we venture into arrhythmias, which will be in a later episode. Now I'll just clear off this writing. So we talked about rate, and now we can move on to rhythm once again. Remember that this little strip over here is very good for determining rhythm. When you have a physical copy of an ECG, what we normally do is fold the paper at the level of one QRS complex over the other and hold it up to the light so you can see how these lines line up to the ones previously. So the ones behind should line up with the ones ahead roughly, because remember that there is a bit of variation with respiration in terms of heartbeat. Yeah, that's about it. Another way you could look at that is count the number of squares, or take a ruler and measure the difference between each of these QRS complexes and then see if they match up. So rhythm is reasonably straightforward. The next part we do is axis, which is a little bit more difficult, and sometimes the clinical utility, the clinical yield from this statistics isn't very apparent at first glance. Now remember the triangle that I talked about in the episode before. If you haven't seen the episode before, just look it up on one of the on Google Images or something. That becomes important over here. We have the 3 leads. That's lead 1, which points from the right arm to left arm, And you have lead 2, which is right arm to the foot, to the legs, and then that's lead 2. And then you have lead 3, which is from the left arm to the legs. Remember that the direction of the arrow is the direction to the positive electrode. And then you have AVF, which is points towards the, pardon my handwriting again, but this one points towards the legs. And then AVL, pointing towards the left arm. And then AVR, which points to the right arm. So essentially, if the direction of the wave is in concordance with normal, which is from the atria to the ventricles in the way the heart is sort of shaped like that, then it's in concordance with leads number 2. As you can see, it goes in the same direction downwards and towards the left, and it's also in concordance with lead 1, and hence that's also positive. That's why in this normal ECG you can see it's positive in lead 1, the QRS complex is positive in lead 1, positive in lead 2, and because it's also in concordance with AVF, you can see it's positive in lead AVF2 as well. These are the 3 leads generally that you need to determine axis, and remember that there are many different ways of determining axis. I usually just look at these 3 leads and determine whether they're positive or not, and that helps me determine where the axis is. Now, if for some reason, say there is and right axis deviation happens in conditions where the right heart takes up more load than it normally does, it just means that the electrical activity in the right heart has gotten a lot more prominent, and not necessarily that the heart has rotated like a clock. So in right axis deviation, you'd see that, once again, pardon me for my terrible handwriting, in here, because it starts to take a different morphology, the right side of the heart would take up a bigger role, a bigger current. This arrow, which normally points this way, starts to point in sort of the other way. That's how I like to think of it. So essentially what used to be in the same direction in lead 1 from right to left is now left to right. So in right axis deviation, your leads 1 will become negative. Despite that, it's still heading towards a sort of downward direction. That's why leads 2 and 3 will still be positive. So 1 is negative, 2, 3 will still be positive. And AVF, because once again it's still sort of pointing down, AVF will also be very positive. And then we can talk about left axis deviation. Sorry about the mess that I've created over here. But in left axis deviation, it means the left heart is taking a bigger role. The electrical activity starts to exceed what it normally is. And as such, What this means is that the arrow, which used to look like this normally, let's label it normal, now starts to look like that because more of the left heart, remember the left is over there, and the left heart starts to take up a bigger role. Now as you can see, it's still in concordance with lead 1, same direction. Hence, lead 1 is going to remain positive because now we're moving away from this lead 3, that'll be negative. And then because now this line over here is away from AVF, AVF will now be negative. Hope that makes sense. In this case, AV leads 2 and 3 may also become negative, but that solely depends on how much the axis has deviated. Remember that because for it to go negative in lead 2, you have to go 90 degrees. So it'll become negative. The lead will become negative in lead 3 first before lead 2. That's the way I think of it. So the difference essentially was in lead 1, it's negative in right axis deviation and positive in left axis deviation. And then we finally have extreme axis deviation. In this case, this arrow that we talked about earlier now goes up all the way to something like that. In which case, 1 was going to be negative and AVF, which normally points downwards, 2 and 3 are all negative. Now once again, as I mentioned, there are other ways of establishing axis, but this is the one that I normally use. And so that's axis. And then now that we've talked about rate, we've talked about rhythm, we've talked about axis, next we talk about the presence of P waves. This is a P wave, and we can confirm that this ECG does indeed have P waves. The first you look at the presence of them, and then you look at their morphology. Normally they're sort of this dome shape, and they in lead 1 it could be broken, so it seems to have like a notch in the middle, so it ends up looking like this very weird shape right over here. And straight after that, then you calculate the intervals, which is, we start off with PR, which is the beginning of the P wave up to the beginning of the Q wave, which is down over here. That's sort of downward deflection. I'll draw it here. So the first interval is the PR, which is at the beginning of the P wave up to the beginning of the Q wave. Then we discuss the P wave. Remember, this should be less than, it's 0.12 to 0.2 seconds long. And then we talk about the QRS wave. We first mentioned the morphology. So as you can see, it goes down to form a Q wave. If it doesn't go down, a Q wave is not present. And the upstroke is the R wave, and the downstroke is the S wave, and that's Q. And the QRS should be less than 0.12 seconds. If it's longer, we call that broad complex. And it can be significant for all sorts of different pathologies, which we will talk about later. And then we have the QT interval. Remember, this is the T wave, that little dome shape. It's normally bigger than P wave. And then the interval from Q up to T, up to the beginning of T, is measured to form the QT interval. It changes with the rate of the heart. And why this is important, hopefully we'll talk about again in the arrhythmias episode. Then finally, we talk about the ST interval and see if there's any changes. Normally this is an isoelectric, it's flat. And in some cases it can be elevated, in which case it becomes significant. Then finally we talk about the T wave morphology. As you can see, these little massive T waves, a lot bigger than the P wave. And you mentioned whether they're upright, whether they're positive above the isoelectric point or negative. And that makes a big difference. So now we've talked about how to, I'll quickly recap. When you see an ECG, you mention the rate, you talk about the rhythm, you find out what axis it is, then you look for P waves, see whether they're present and what their morphology is. After that, you talk about the PR interval. Following this, you talk about the QRS, the morphology, and then the interval, the length of the QRS. Then you also mention the ST segment, and then finally the presence of T waves and their morphology.